Hey guys, welcome to 14.4b. In this lesson, we're going to be looking at solving more trigonometric equations. And specifically, we're going to look at some examples with modifiers on theta. So for example, 2 theta or 3 theta or something like that, and how you handle that type of trig equation. So make sure that you have a note sheet out with the section, the date, and the I can statement. And then resume the video as soon as you are ready. All right, so for our first example here, we're going to look at solving this trig equation, 2 sine of 2 theta equals 1. And specifically, we're going to look for answers on the unit circle this time. So if you think about this problem, it starts out fairly simply. We're just going to divide by 2 on both sides so that we have the sine of 2 theta equals 1/2. And then the next thing that we want to do is we want to take the sine inverse on both sides to get 2 theta alone. So we'll have 2 theta equals the sine inverse of 1/2. So now here's where things are going to get a little interesting because of this modifier. So I'm actually going to do this incorrectly first in red. And I want you to see, because I want to do this incorrectly first because this is what students often do. And so this will be something for you to try to avoid. And hopefully you'll see that here. So I'm just going to write off to the side here. This is the incorrect way to do this problem. The next thing you would do is you would take the sine inverse of 1/2, and you would think to yourself, okay, on the unit circle, sine inverse of 1/2, so 1/2 occurs for sine at pi over 6 and 5 pi over 6. So we would say 2 theta equals that. And then we would divide both sides by theta. We would get theta equals pi over 12 and 5 pi over 12. And the issue here is that if you think about this, both of these answers are correct, but they only cover a small fraction of the unit circle. So we clearly need some more answers because we probably all of our answers on the unit circle aren't going to occur just in the first quadrant. So instead, the way to actually approach this problem is we are going to take the sine inverse of 1/2, but we need to write it in its general form. So we're going to write 2 theta equals pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. And the reason we need the general form here is because now when we divide by 2, we're also going to be dividing the 2 pi k by 2 as well. So we're going to get theta equals pi over 12 plus pi k and 5 pi over 12 plus pi k. And what this allows us to do is now we can iterate through all the different values of k to come up with all the possible answers on the unit circle itself. So for example here, we would have theta equals obviously pi over 12 when k is 0, and 5 pi over 12 when k is 0. So these two are each option when k equals 0. But now if k equals 1, we would have 13 pi over 12, because pi over 12 plus 12 pi over 12. And if k equals 1 for the second one, we'd have 17 pi over 12. So this is when k equals 1. And so then the last thing you need to check is you need to keep going until you get beyond the unit circle. In this case, k equals 1, not 2. In this case, if you were to try k equals 2, that would be 2 pi plus pi over 12. And right away you can see there you're beyond the unit circle, so you're done. So these 4 answers then would be your 4 solutions to this problem. So you'll notice if you do it incorrectly and don't include the general form, you get some of the answers, but not all of the answers. So let's look at another example here, another couple examples actually. So I have 2 examples on the board. I'd like you to pause the video and try both of these and see if you can solve them on your own. See what you can come up with here. and then resume the video when you're ready, and we'll go through it and see if you come up with the same thing that I came up with. All right, so for the first one here, I would take the cosine inverse of both sides. So I'd have theta over 2 equals the cosine inverse of -1. And so now the cosine inverse of -1 is pi. So I'd have theta over 2 equals pi plus 2 pi k. And then we're going to multiply through by 2. So we'd end up with theta equals 2 pi plus 4 pi k. So now we need to start checking to see if any of these fall on the unit circle. So for example, let's say k was -1. If k was -1, we would end up with -2 pi. 2 pi minus 4 pi, which is clearly not on the unit circle. If k equals 0, we would end up with 2 pi, which is also not on the unit circle, because remember the unit circle goes from 0 to 2 pi, but 2 pi is not included. And if k equals 1, then we end up with 6 pi, which is not on the unit circle. So in this case, and I could go further, but I don't have to, because they'd all not be on the unit circle. So this problem actually has no solution, because there's no value for k in which we would get an answer that's actually on the unit circle itself. So let's look at the second example here next. So for this one, we want to start out by taking the sine inverse of both sides. So we would have theta minus pi over 4 equals the sine inverse of 1. And so now, again, we want to think about, okay, what value or values make 1 when you take the sine. In this case, the only angle that does that would be pi over 2. So we'd have pi over 2 plus 2 pi k. And as a reminder, just make sure you remember if you're doing any of these problems with tangent, that one will have pi k rather than 2 pi k as its period. So now we need to add pi over 4 to both sides. So theta equals 3 pi over 4 plus 2 pi k. So I'm just adding 3 pi over 4, or adding pi over 4 to pi over 2. So now, if we think about this and like iterate through this, we would have theta equals, if k is 0, theta equals 3 pi over 4. If k is 1, we would have 3 pi over 4 plus 2k, which is too big. So in this case, theta equals 3 pi over 4 would be our only solution to this problem. So our final example here that we're going to look at, another one that actually doesn't have modifiers, but is just a slightly more tricky problem that gets kind of interesting. So take a look at this problem. Sine theta plus cosine theta equals 1. So there's an issue here, right? And the issue here is that we have two different trig functions, which makes it much harder to solve it. So our goal in this case is probably to come up with a way to use a Pythagorean identity to get rid of at least one of the two types of trig functions. So typically when you see two trig functions, often your goal then should be to try to use a Pythagorean identity. The issue is that Pythagorean identities require squared values. And in this case, let's see if we can fix our spelling here a little bit. In this case, we don't have any squared values. So we probably need to square both sides to create square values. So I'm going to start this problem out by squaring both sides. And if I do that, on the left side, we would end up with sine squared theta plus 2 sine theta cosine theta plus cosine squared theta equals 1, because 1 squared is 1. So now this is where we start having to really understand and recognize a lot of our identities. In this case, sine squared theta plus cosine squared theta is just 1. And 2 sine theta cosine theta, that's one that you should recognize as sine of 2 theta. That's one of our double angle identities. So in this case, we actually have 1 plus 2 sine 2 theta equals 1. So now we can subtract 1, sine of 2 theta, not 2 sine of 2 theta. So now we can subtract 1 from both sides, and we would end up with sine of 2 theta equals 0. And so that means that 2 theta equals the sine inverse of 0. And the sine inverse of 0 occurs in two places, at 0 and pi. So we can say that 2 theta equals 0 plus 2 pi k and pi plus 2 pi k. So now when we divide by 2, we're going to end up with theta equals 0 plus pi k and pi over 2 plus pi k. So if we go to list out all our answers then, if k is 0, then we would have theta equals 0 and pi over 2. But if k is 1, then from the first one we would end up with pi, and for the second one we would end up with 3 pi over 2. And as soon as k is 2, then we've gone too far. So these would be our solutions within the range. But this problem asked us to also find the general solutions as well. And the general solutions to this one, if you look at this, we've got 0, pi over 2, pi, 3 pi over 2. We've got all 4 corners of the unit circle, which means we can iterate around in quarter turns to come up with our answer. So our general solution would be theta equals pi over 2k is the general solution. So that brings us to the end of our video for 14.4b. Tonight's homework is a packet that you're going to start, but you don't need to finish. We're going to finish it in 14.4c as well. So it's a multi-lesson packet that you're going to be working on, and the packet and answer key are posted for you.